Good morning, friends. Myself, Dr. Atul Nagpure, Assistant Professor, and today our topic is Application of Chelating Agent in a Chemical Analysis. As you are all aware that chelating agent find many applications in numerous sectors. When metal ion form a complex with a ligand, there is a significant changes occurs in the properties. It can be color, solubility, stability, and so on. And sometimes it has been observed that the specific ligands has a different interaction with the given metal ion, and all these kinds of aspects can be used for separation of the metal and analysis of the metals also. Now in this sector, in this lecture, we will try to give overview of the applications of the chelates in the chemical analysis. So first we have applications in inorganic qualitative analysis. Second, we have spectrophotometric analysis, and the third as extractor, and the fourth as precipitant, and fifth one we have as masking agent. Now let's start with the first one, inorganic qualitative analysis. Now while doing practical in a chemistry lab, sometimes we require to analyze the metal type, because in a given solution various kinds of metal may be present, and that will be in a very minute concentration. In such cases the chelate plays a significant role, in which this will be help you to estimate the concentration as well as a quality of metal ion present. Now in this we will try to see how we can estimate nickel using a chelating agent, and the name is DMG as a ligand. Now let's say that we having a nickel plus 2 ion in the solution, and which is have a very less concentration. Alright, so the concentration of this is very less. We have very less concentration, and this less concentration nickel plus 2 ions we have to identify. And for this, generally DMG ligand, this is called dimethyl glycine DMG ligand. I'm writing a name below that, dimethyl glycine. This ligand is used, and this ligand is actually a bidentate ligand. This is a bidentate ligand. Now, right, when this nickel plus 2 ion form the complex with DMG, what they will do? They will form a complex, and here we require 2 mole of the DMG. So write down 2 mole of the DMG here. So the resulting complex will be nickel DMG2, clear. And here remember that when we take a DMG actually carry -1 charge, and hence this will have nickel plus 2 charge as we know, and the whole complex now will be have a 0 charge. Keep in the mind. And if I write down the structure of this, nickel DMG is actually a complex, and in which we have this. Let me write down the structure first, then we discuss. Just a minute. We have carbon single bond N, and we have double bond N here, and double bond N, and we have methyl and methyl. I'm writing this is, we have methyl, okay, and here we'll be having O minus, and here we have OH. Here we have OH. So what happened if I remove this H and write down the OH here? This is actually a DMG ligand. But if I treat this molecule in the basic condition, we'll remove one OH and O carry a minus charge. That's why I told that one DMG carry a negative charge, right? Now in this case, if you look at very carefully, since we have nickel metal, now they're going to try to form a complex with this and writing nickel plus 2 at the center. Okay, and again the structure I'm writing here. So we have N, again here N, so double bond carbon, carbon and double bond, right? And here we have methyl and the methyl, and this is will be having here OH, and now here we have O minus I. So the lone pair on the nitrogen now will use to form a bonding with the nickel plus 2 ion. So you can see here this two center nitrogen, and now they're going to form a bonding with the nickel by coordinate bond, right? And this is also formed. So the one molecule form the two bonding here, right, via nitrogen center. Now if you look at very carefully here, this O minus now try to form the extra interaction with this proton, and this is occurs via hydrogen bonding. Here is the same thing. Now they will try to form a bonding, and this is this complex is actually a red color complex, color complex, and this is the way we can able to estimate nickel as a nickel DMG complex. In this case, we have nickel is in a plus 2 state, and this is a 3D8 system, and this is actually a square planar complex with DsP2 hybridization. So in the first, when a metal is in less concentration, we can able to form a complex from the given metal, so that it's going to form a compound which is has a color. So by performing this kind of analysis, we can able to estimate even very less concentration of metal ion in the solutions by forming a suitable complex. And this is the structure of the nickel DMG complex, where nickel is coordinate through 4 center and has the square planar geometry. So I'm moving for further, and next we have a spectrometric analysis. Now just I have told you that many complexes of metal ion with the chelating ligands are colored in nature, and that's why this property can be used to find out the concentration of the various metal. Now here in this technique specially, we use a colorimetric analysis, and we also use a spectrophotometer or spectrophotometry. Now here in a colorimetric analysis, remember that it is used for visible rays, whereas spectrophotometry can be used in a various region. Now with advanced technology, this can be applied in the various rays, including X-rays. It can be used in ultraviolet rays also in a visible range, and it can also be used in a infrared, right, and the microwaves. When we are using colorimetry in this, generally a colored compound is analyzed. Remember, generally colored compound is analyzed, and if you are using spectrophotometry, in this case we can able to measure a colored as well as a colorless compound. This is a very important. Now so if some compounds are not colored, in such cases we have to use spectrophotometry. Now the question here, how we can proceed? Suppose again same thing, given metal ion form of complexes with the chelating ligand. Now question here, how we can able to analyze the concentration? There are two techniques are available, colorimetry and spectrophotometry. For if you want to apply any of this technique, you have to first find out the lambda max of the solution. Suppose, let's say, first will be how we can able to measure the lambda max. A lambda max is the wavelength at which the substance or the compound absorbance is maximum. So I can say that at particular lambda max the sensitivity is high. So imagine that we have various wavelength, and this wavelength we have to optimize. This will be nanometer, right? Nanometer, and I'm plotting. This is on x-axis, and here this is on absorbance. Okay. Now imagine that we have 5 solutions, and for first solution at this particular wavelength 1, 2, 3, 4, 5, if I got the absorbance here, and second time I got absorbance here, third time I got absorbance here, and the fourth and fifth time, so we'll get a kind of this curve. Suppose we got. Now if you realize very carefully, at this particular wavelength, the value of absorbance is maximum. Now since value of absorbance is maximum, this is called as a lambda max, right? So first thing will be, you need to measure the lambda max of the given solution. Lambda max says that compound has the maximum absorbance, and this both the instrument works on the basis of Beer-Lambert law. This is a very important law in spectrophotometry and polarimetry. Beer-Lambert law. What Beer-Lambert law says, the absorbance, A is absorbance, is equal to epsilon C into L. So this law means the absorbance of any substance, A is absorbance, epsilon is called molar absorptivity, C is the concentration of the substance in the solution, and L is called optical path length. So if I look at here, so first objective will be, if you are using this technique, you need to measure the first absorbance, right? And absorbance, you require a lambda max. Afterwards, once you finalize the lambda max of the solution, you have to use the same lambda max and need to draw a calibration curve. And the second is called developing a calibration curve, because a calibration curve is required in order to analyze metal in a quantitative manner. So again, so whatever lambda max we have, we'll use now same lambda max here, and again we'll find out the absorbance of the solution. But here will be the concentration. Remember, here will be the concentration of the sample on the x-axis. So what we will do, we will take a known concentration of the substance, and say again we have 1, 2, 3 or 4. So in the lab we have prepared a 4 different concentration, which concentration we already know, and at this particular wavelength, now we're going to find out the absorbance of the solution. So let's say that this is the absorbance of the solution we obtain at a particular, means same. Here I am recording by keeping the lambda max same. Remember the point. So now if I got a curve, imagine that I have got this kind of curve, right? So by using a calibration curve, if you are wanted to analyze the unknown compound concentration, now we can do that. We can measure the absorbance, and let's say this is the absorbance of the unknown. So I can write down this is my unknown compound, right? And this is my unknown compound we have it, and this is the absorbance we know, right? And if you know the absorbance now, we can able to find out the concentration here, and this is the way we can use this law. So whether we are using colorimetry or spectrophotometry, you have to use a Beer-Lambert law. But in both the cases, firstly you need to finalize the lambda max of the solution, and then by using the same lambda max, you have to develop the calibration curve, and with help of that, we can able to analyze the given metal ion, right, properly, and by using this curve, and you have absorbance and corresponding concentration we can able to get. And this is the way how we use a spectrophotometric analysis. Now we'll move for third, extractant. Extractants, in such a technique, generally solvent extraction and ion exchange chromatography is used. Now let's consider that in a given solution we have two metal ion, and one metal ion is Fe plus 3 ion, and the second metal ion is iron plus 3 ion. So let's consider that we have Fe plus 3 ion, and plus aluminum plus 3 ion, right? And this is in a aqueous solution. So this is you need to remember. But we know that these two metals are there, but we are not sure about the concentration of these two ions. Now in such case, we have to use a specific kinds of ligand, and by maintaining the pH condition. So I am using the pH value nearly equal to 3, and here using 8 hydroxyquinoline, 8 hydroxyquinoline as a bidentate ligand. I am writing the structure here for your convenience. Let's say we have quinoline here. Okay, this is molecule we have. This is quinoline, and at 8th position we have hydroxy. This is called 8 hydroxyquinoline, right? And this is generally referred as oxynol. This is also called as a oxide, and this is a bidentate ligand. This is molecule is a bidentate ligand coordinated via oxygen and nitrogen. So when we are maintaining the pH 3, what we can do now, we can form a complex of these two. But interestingly, in the first cases only Fe ion form the complex. So we'll be having oxide 3. Now here we have plus 3 charge, right? And remember that when we are using 8 hydroxyquinoline, in a basic condition this will be removed and O will carry minus charge. So one ligand can carry a minus 1 charge, and hence we are complex 0. Afterwards, what we'll do, we will extract this in a chloroform, because a chloroform is organic solvent, and this compound has higher solubility in an organic solvent, and we can extract in this chloroform organic solvent. Afterwards, once we extract in a organic solvent, now afterwards Al plus C ion can again form a complex with this ligand, and this will form in this kind aluminum oxide kind of complex, right? We have 3 and again plus 3 charge, again charge on 0. So the point is that here, firstly I can able to form complex with the iron, and secondly, so once I form complex with iron, I will extract by using suitable organic solvent like chloroform. I will remove from the reaction mixture because the solid compound. Afterwards, again I can able to find out a complex. I can able to form complex with aluminum plus 3, and I can do in a step by step. This is how we can able to use the chelating agent as extractant here, and based upon that, separation and purification of this compound is possible. Furthermore, for your knowledge, the ethylene diamine tetraacetic acid is a well-known chelating agent for purification and separation of various lanthanides, because lanthanides can be easily separable by using ion exchange chromatography. So now next we will discuss next topic is as a tracy pattern. Now sometimes it has been observed that we can able to analyze the compound by forming their compound table. So if you have analyte, imagine we have analyte, and let's say now analyte is nothing but a nickel plus 2 ion we have in here. So if I convert nickel plus 2 ion into a sparingly soluble salt, I can able to weight this compound, and after that I can able to find out the weight. So just imagine that we have nickel DMG complex, right? We have plus 2 charge and we have 0 on the complex. So I need to analyze nickel here. So if I convert nickel into the sparingly soluble salt compound like nickel DMG, this is a compound. So from the ion, right, this ion was in solution. I have converted this ion into the stable compound, and from the stable compound now I can able to find out the concentration of nickel plus 2, right? And this is actually known as a gravimetric analysis. Gravimetric analysis means the ions we will convert into the suitable sparingly soluble salt, which is the solid compound. We have to measure the weight of this compound and find out the weight of the ion in the solution. This is the way we can able to find out the concentration of unknown compound. And next and last we have the as a masking agent. I hope that you are aware that many calcium ion, right, and the magnesium ion, they form complex with the EDTA ligand, right? But sometimes we have to use a specific ligand for some ion. So let's consider that we having this 3 ion and we have to use a particular. So if this ligand form complex with this, for extracting silver plus ion, now you have to use a specific ligand which will not going to interfere here. So the selection of ligand is very essential. So this is what all about was the application of chelating agent in a chemical analysis. Thanks for watching. Good luck. Have a nice day.